Good afternoon. So in the last couple of lectures, we have looked at the white noise limit, right, in one dimension, where we said we have an ODE for a slow variable x, and then which is being forced in Langevin style by a fluctuating process that is much more rapid, right? That's why relative to x, but is correlated. So we can still treat the dynamics of x with an ODE, non-autonomous ODE. But then when the timescale separation, right, goes to 0, I mean, in other words, the timescale separation increases, right? So the ratio of timescales epsilon goes to 0. We wanted to derive the effective SD to see how the forcing in the white noise limit appears. So just to recap, right, we'll do this. I want to recap what we did in the last class, which was in one dimension. And then I will show you the analogous results in multi-dimension. And the important thing is that when you go to multiple dimensions, the limit is not necessarily Stratonovich. So that is the important point of this lecture. But to set things up, it's good to recall in one place what we have done over the last few lectures in 1D. Okay. So that's what we have here. Yes, so we think of this ODE for x, right, which is got a deterministic part, which is just this is just some nonlinear ODE. So this is all the stuff that is dependent on, could be dependent on x, for example, right? Some function. But then we have this forced part, right, where this alpha is, we took to be some Markov, continuous Markov process. The 1 by epsilon is what tells you that it's fluctuating much faster than this dynamics would lead to, okay? So what is alpha now? Alpha is itself given by an Ito SD. We can always write such a thing down for any alpha you cook up, right, as long as it's a continuous Markov process. So this means the alpha does not necessarily have to be generated with some SD. You can generate it using random numbers with some algorithm. As long as it's continuous Markov, you can write in principle something like this down, right? And it's only in principle that matters because we will never use these coefficients of this SD, right? So, but in principle, we can write that there's an SD for alpha, right, with some coefficients A and B, right? A is the drift part, B is the Brownian part, right, the coefficient of the Wiener increments. And these coefficients can depend on alpha, they can depend on time. The important thing is that this SD leads to a stationary process, right? So, so that this SD should ultimately lead to some stationary process for alpha where the statistics no longer depend on time, okay? So then it's important that I don't have the time here. Otherwise, for some arbitrary time dependence, you can keep having fluctuating statistics. Okay. So for simplicity, let us just consider this. So the A and B depend only on alpha. Now, in such a situation, the A and B should be such that alpha ultimately reaches stationarity. Right? That means if you look at the Fokker-Planck equation for just the alpha process, it will ultimately lead you to some steady stationary solution. Okay, but what I want to give as an input is not the A and B. My derivation, as we saw, doesn't really depend on this. In the end, what will appear is only the autocorrelation of the alpha, which of course is a consequence of this, but I don't have to input that. What I have to know as an input is the integral 0 to infinity of the autocorrelation function. This is what I need, so I call it capital D. Okay, so I start with this. So really, if you want, you have the ODE for x driven by this fluctuating signal alpha of t. And all you need to know is the autocorrelation of that alpha, okay? The integral of the autocorrelation from 0 to infinity. Then if you know this, what we proved, right, in using center manifold reduction is that in the limit of epsilon going to 0, right, where the scaling has been done in such a way to give you the white noise limit. So when you go to epsilon equal to 0, you can show that if I go to the Fokker-Planck equation and I consider the PDF, combined PDF for x and alpha, and then I take the marginal distribution after averaging out alpha, that I call phi. So this is another probability distribution for the dynamics just in x and time. So I can derive the following equation, right, in the limit of epsilon going to 0 directly for phi, a Fokker-Planck equation only for phi, right, by averaging out the alpha direction using the center manifold reduction. When I do that, I get the following equation for phi. So this is the key result, right? So you get a drift term. Sorry, this should be phi. Yeah, so you get a drift term, right, which is directly the drift coming in x. So remember, this is the Fokker-Planck equation now for the x process. So the drift is what you read off here. That makes sense. But now this was originally part of the drift itself, right, with some alpha sitting there. Now averaging out alpha has transformed that drift term, okay, which was dependent on the fast direction. If you like, the drift velocity depended on the fast direction. When you averaged out, just like a Taylor-Harris dispersion, that gave you a diffusion in the slow direction, right? So that drift became a diffusion term. So you see two derivatives sitting there, right? And with this diffusion coefficient B. Okay, so what was a drift but alpha-dependent drift, right, became a diffusion in x with this B coming in as the B square really effectively is a diffusion coefficient. And what you found is that this diffusion term with space-dependent diffusivity was written in this nested form, which really corresponds to the Stratonovich Fokker-Planck. Right? The way to see this is you can split this derivative and write it so that you get d square by dx square, that becomes the Ito term, and then you get an extra drift. Right? And this is exactly the drift that one would have if you took a Stratonovich equation and converted to Ito, if you remember, right, in the earlier part of the course. So the final Fokker-Planck in the Ito form, if you like, right, it has got a drift which has the part from A and an extra part involving B. That extra part is exactly the extra Ito drift that comes, when you convert Stratonovich to Ito. Right? And then you have the usual Ito diffusion term with B square. And what's interesting is that in addition to this B coming in as so the strength of diffusion depends not only on this coefficient, which was in the original ODE, right, is the coefficient of the white noise. Right? Not only that coefficient squared, the white noise process, its integral of autocorrelation is also coming in, right? So if I normalize alpha to be 1, then D would be 1. Okay, but or half. If I normalize it to half, I'll just get 1 by 2. But if you leave it, then you'll get D, right? And the D is sitting here. So obviously now to make it consistent with the proper Fokker-Planck equation, for which I can write in SD, this 2D is not okay, right? I need 1 by 2 times something diffusion coefficient. So obviously I can write 2D as root 2D the whole square. Okay, when I do that, I can split the root 2D along with the B's. So the real diffusion coefficient is root 2D into B. Because then similarly in the drift term, I have two B's, I have this root 2D, it's a constant, right? So I can write this as root 2D into root 2D and keep each root 2D with each B, right, here and here. Or I can directly do it here, right? I can take this root 2D into root 2D and keep one here and one here. Okay, so because D is a positive constant, I can do this. If D was negative, of course, I can't do it, right? But D is going to be a positive constant from here. So in 1D, right? So then I can do this. And so looking at this, either this Fokker-Planck and recognizing it's the Stratonovich form, or looking at the Ito and recognizing I have the correct drift, right? I can take this Fokker-Planck equation, write the corresponding Ito equation, and then recognize that, oh, this is just the Stratonovich drift. So therefore, the final SD is the following, which is a Stratonovich SD. Okay, so I have the original drift in the ODE. So the deterministic part of the ODE directly comes into the SD as the drift. And the white noise part comes in as a Stratonovich noise. Rather, the colored noise, which I am taking the white noise limit of, becomes a Stratonovich white noise. Okay, with the same coefficient B, but now it's also multiplied by root 2D, where D is this autocorrelation. Okay, so that was what we proved in 1D. Okay, so in one dimension, when you take the white noise limit, you get Stratonovich. This is what we had also anticipated with the geometric random motion exercise we did in class, right, a while ago. So now we understand why we got the Stratonovich limit when we took this geometric random motion problem, and we have in fact proved it in some asymptotic way. Okay, so now what I want to do is ask if we are in multiple dimensions, right? So that means so it could mean that I have a vector x, right? So many slow processes, and a vector of alphas, many fast processes in the general case. But what's important for us is having many alphas. If you have many x, nothing will change in the problem, right? The main nuance comes if you have many noises. So we'll for now just consider the case where I have only one slow variable x, but instead of it being forced by just one alpha, you force it by a vector of alphas. Okay, so you have different fast processes, and those fast processes could be interacting with each other. Okay, so the example that we are again driving on to in the whole course is turbulence. Right? If you consider some variable x which is being affected by a turbulent flow, the turbulent flow is not just one number. Right? Even if you want to approximate a turbulent flow field, it's a field. So one way to do it, of course, is to write the spatial field as a sum of Fourier modes. Okay. So example, sine x, sine 2x, sine 3x, and so on, the cosine modes up to some cutoff. So you can have some approximation for the velocity field, turbulent velocity field, or turbulent shear stress, or whatever is the turbulence that is affecting your x variable. Okay, so you take that turbulent object and expand it in a Fourier series. The coefficients will be noises. Okay, so then I can say, okay, actually the turbulent flow is coming from the Navier-Stokes. I'm going to approximate that away and replace it by some noisy field. In the end, what you will have is coefficients of the Fourier functions. Right? So all those coefficients are noises. They are separate alphas. And all those alphas are affecting your x. And the alphas can be evolving with each other. So the alpha need not be alpha 1 separate equation, alpha 2 separate equation. Right? You will have a single vector equation for alpha. This can have alpha 1 term, alpha 2 term. Right? The noise also can combine because the alphas are in fact coupled in turbulence. So I can come up with some, again, I don't have to actually generate the turbulent field using some SDs. Right? I can generate it however I like, but as long as it's Markov, I know I can write it in that fashion. That's what I wanted to remember. Right? So that's a good example to keep in mind. So if I have this variable x, it's being forced by a turbulent field, then it's being forced by many noises. Okay, and then the question is, in reality, the turbulence is finitely correlated. So I should write a set of ODEs just like this, ODE plus SD. But then if I want to get some analytical results in the white noise limit, if I start making the assumption that the turbulent flow is fluctuating much, much faster than my slow process and take that time scale separation to infinity, with epsilon going to 0, will I get Stratonovich? Okay, so it's the same question, but now when the noise is multidimensional. So what we'll do is let me write down sort of these main results. Okay, in fact, the derivation will proceed exactly the same way. The nuance will come when we hit this Fokker-Planck equation. Okay, so let's see that. But just to make things concrete, I'm going to write down the multidimensional version. Okay. So we'll have an alpha I now. Okay, an alpha vector. So now let me formulate the problem in the same way. Okay, instead of having dx dt, I'll have a vector dxi dt that is going to have a drift function ai. So ai is a function of xi and t, right? So the ai is not a constant; it's a function, just like it was there. I'll skip all this off arguments and so on because as it is, I'll have to introduce notation. So yes, and then I have now b, right? So here b was one coefficient multiplying one noise. I now have a vector of noises which I can combine in some fashion. So I should have a matrix. Okay. So I'll have bij multiplying by this alpha j upon epsilon. Okay, so now this alpha is a vector of correlated fluctuating processes which are being combined in some way through this matrix. This matrix itself is a function of x, right? Only then the question of Stratonovich and so on will come. Okay, and now I have the equations for alpha, which will be a set of SDs that I can write down, as I said, in principle. Right, in the same fashion. Okay, so again, at least this I can write down in principle, and the important thing is when I come to d, right? So I'm going to now have, where I had just one constant d, I will have again autocorrelation between the vector components. Okay? So what you will find being relevant instead of just d is now dij. That is again integral 0 to infinity dt of alpha I at t, alpha j at 0. Okay, and this dij is not immediately, you cannot just interchange I and j, that would be important, right? Because the way it's defined is the first index corresponds to the guy evaluated at time t. So alpha I is at time t, alpha j is at 0. If I do dji, it's not the same because then alpha j will be at t. Okay? And that's because in general these are not, it's not the same thing, right? The noises are corresponding to different physical things. So if you think of the turbulence example, right? And I do, the alphas are the coefficients of some Fourier modes of a turbulent velocity field. Right? Now the large scale Fourier mode like sin x, right, which spans, so sin x is something that varies slowly. It's a leading mode, right? Larger mode than that is just a constant. Okay? So you take 1 and then cos x and then cos 2x and so on. Right? So if you look at the small wave numbers, right, in a function, periodic function that is done, of which you do a Fourier decomposition. Right? So I take sin x, cos x, these are the large, slowly varying things. Right? So that would be, let's say, alpha 1. And then alpha 100 would be sin 100x, which is highly fluctuating. So I think of the alphas as coefficients of, right, different Fourier modes, different wavelengths. They're not the same. Right? So if I look at a correlation between 1 and 10, right, this is basically saying what is the correlation between a large scale mode, right, at a future time, given that the small scale mode had some value. Right? So how does a small scale mode affect the large scale mode forward in time? The reverse is obviously not necessarily the same thing. Right? So you can see they are not, you should not think of this as just some innocuous alpha 1 and alpha 2 are the same. Then this will not make any difference. Right? But what you're really saying is that in general it could be very different processes. Right? So that alpha 1 affects alpha 10 and alpha 10 doesn't affect alpha 1. Because that's going to play an important role. But you can already see that in the turbulence example, how this is going to be relevant. Okay. Or in any other process where these alphas are quite different, right? They're not just the same thing. Okay, so let's keep this definition in mind. We'll come back to this. But that's the setup of the problem. So now, analogously, if you keep in mind the 1D thing, the derivation generalizes the same way. Because what I need to do is look at the PDF, right, in this high dimensional space. So in x, comma, alpha 1, alpha 2, alpha 3, blah, blah, blah. Right? But whereas earlier I just had one fast direction, I have many fast directions corresponding to all the alphas. But this is not a problem, right? I can formulate the same center manifold reduction. This time, instead of taking the linear operator to be the Fokker-Planck only in alpha, I do it, the multidimensional Fokker-Planck operator in the alpha 1, alpha 2, alpha 3, and so on in that multidimensional space. Okay. And the Fokker-Planck equation is like a diffusion operator, just like you have 2D diffusion, right? If you have 1D, you have d square by dx square. When you have 2D, d square by dx square plus d square by dy square can be taken as one operator. And then you can get eigenfunctions for that by doing sin x, cos x, sin x, cos 2x, and so on, right? So this is called direct product spaces. So in the short message is that you can take all the alphas together, right? Look at their Fokker-Planck operator, which is all the fast directions. You can define again the L1 operator as we had done before. This will now have diffusions in all the alpha directions. But you can do the same center manifold reduction. And you'll get essentially the same results, but now we have to account for the multidimensional nature. So I'll skip the details, but basically if you use Einstein notation and this direct product space idea, you can carry out the same 1D derivation up to a point. Right? So that's what I want to make. So let me, because there are several indices, I'll just copy this down. Okay, so in the same way, I can proceed, right? And when I get epsilon going to 0, I'll get the equation for the marginal distribution phi after averaging out all the alphas. So phi again is just for the single x, right? Right? So I get the effective Fokker-Planck equation only in the slow direction. So I now have dou by dou, sorry, x. So I could have generalized this to xi, but let's do x for now. I think I wrote xi, right? Let me check. So I had already written xi. Fine. So we'll proceed with xi. Okay, but what's important, as you will see later, is mainly the fact that alpha is a vector. So don't get confused between this I and that I. Right? It's just in every formula a separate index. So this is multidimensional because you're taking a vector of alphas. Right? The x could be just one x or several different x's. Okay, so let me write the formula now for having a vector of x's, right? Just so that you have the general result. So this is indeed xi and xi at 0. So now D you see comes in just like before, but now it's a matrix, right? So it has two indices. The B is there like before. Okay, so this is the drift. I'm writing it directly in the Ito form. So you would have derived it. It looked like Stratonovich, and you can separate it out, right? So that you get what looks like an Ito drift, but we have to be careful. Okay, but anyway, you have that term. It's the analog of what you had in 1D. But now this is a tensor. This is also a tensor. So multidimensional diffusion operator. So again, half and 2, I'll have 2D here, but it's a tensor now. So up to this point, you can reach by doing the same center manifold reduction, okay, but just going into multiple dimensions, multiple alphas. Right? But you can use the same linear operator theory now in this direct product space of alpha 1, alpha 2, and so on, and you can derive this result. Okay, the question is now, how do we proceed from this, what looks like a priori some kind of Fokker-Planck equation, to an HD? And this is where we'll encounter a problem we didn't have in 1D, okay? Because, so if you, let's look at the diffusion, nominally what seems like a diffusion term, right? What we had done is to recognize it to be a Fokker-Planck diffusion operator, we had to have a diffusion coefficient like B squared, right? Or some diffusion coefficient squared has to appear, or rather the diffusion coefficient has to be something squared. Right? So this is d square by dx square of, I should have diffusion coefficient phi, but the diffusion coefficient has to be something squared. Then I can convert it to an SD, where that something which is being squared becomes a coefficient of the Wiener process. The problem is that now I have B into B, right? So this is a matrix, it's B transpose, but again multiplied with this D. So it's like B matrix, D matrix, B transpose matrix, okay, in this way. So that is still okay, provided I can split the D. Otherwise, I cannot write it as something squared, right? Right now, it's something like B is a matrix, D is a matrix, B transpose, something like this. But that's not what I want, right? What I really want is something like this. So I want to be able to write D as nu transpose. In other words, I want to get some kind of square root of the D matrix. Right? By square root of D matrix, you mean you can write the matrix as some other matrix times its transpose. Okay? If I can split D, then I can keep nu with each B, and then I will say B into nu is the diffusion coefficient. That would be the multidimensional analog of what we did in 1D. In 1D, this was a non-issue because D was just a scalar positive constant. I can just write D as square root of D the whole square. Right? in the moment D becomes a matrix, you can't do this unless you can split D as nu transpose. Right? If I can split D as nu transpose, then of course I can write this like this. Okay. The problem now is, what does it mean what should D be for me to split it in this way? Right? If this is true, D would be symmetric. Right? So you can only take a square root of a matrix if it is symmetric. Okay, so right, to be a Fokker-Planck equation, dKl has to be symmetric. That means dKl is equal to dLk. And this, as we just discussed a moment ago, is not necessarily true. Okay, because if this is symmetric, right, it would mean that the autocorrelation of the L noise at time t with the autocorrelation of the K noise at time t with the L noise at 0 is the same if you flip it in time, right? But we are just discussing that need not be the case. We'll come back to physically when this is true or not, but as of now, we can say that if you have a vector of noises, they are integral of the autocorrelation matrix itself, and then therefore the time integral, which is this, need not be symmetric, right? Because these noises are not the same, they're very different processes. And one noise process can feed into the other one and not vice versa. Okay. I mean, you can obviously construct such a situation, right? You can have a vector of noise, just take two, right? L1 and L2, or alpha 1 and alpha 2. Okay. Alpha 1 equation is independent, only depends on alpha 1, but the alpha 2 equation has alpha 1 in it, like a drift. Right? Then obviously alpha 1 will impact alpha 2, but not vice versa. So then you can always construct situations where this is not true. So then you cannot directly split this D here and here. And that's where we have a problem, where the multidimensional one, it does not follow like 1D. So what you can always do, okay, is write dKl in terms of its symmetric part, right, plus its antisymmetric part. Right, or you write D in terms of, you can decompose any matrix, right, into symmetric and antisymmetric, right, just by adding it with its transpose and subtracting its transpose. And what's interesting is now if you substitute this here, what you will see is because you don't have this D by this product by itself, it's also taken the inner product with these derivatives, right? Ij is coming here. And if you look at the nature of the derivative, I can of course swap, right, these two. So I can replace I and j in this derivative, you'll get the same answer. So that property, because this D appears inside these derivatives, you can show that this full D, this quantity, is the same as if I replace dKl by only its symmetric part. That's because the antisymmetric part, when you take the derivatives and use the fact that I and j, the derivative can flip, you will knock it off. Okay. So this antisymmetric part of D doesn't contribute anything to this diffusion term. So I can replace this dKl by its symmetric part. Okay. I cannot do that here because I don't have two derivatives. Okay. I mean, I have two derivatives, but this and this don't interchange. It's because these two are sitting outside, I can just flip them. Right, here I have got something in between. Okay. So I can replace the D by its symmetric part only in the diffusion term, not in the drift. So what does this mean? This means that, so dKl can be put dKls in the diffusion term, but not in the drift. Okay, so I've not shown you the derivation, but it uses the fact that this x and j in the diffusion term can be interchanged. Okay. This and other things of the discussion that I'm saying now are in a paper by Bo and Chalani, Physical Review E, I think. It is in the following PRE paper, okay, where they consider this multidimensional limit of the white noise and show the results I'm going to discuss today. Okay, so the point is I can replace this dKl by its symmetric part here. Otherwise, I could not even call this a Fokker-Planck equation. Right? So now I know that when I do that, I make this symmetric. Then I can decompose D into nu transpose and take a nu with each B, right? And so I'll get a proper diffusion operator. And so I could now call this an Ito Fokker-Planck equation, because when I translate it to an Ito SD, I'll have the correct diffusion operator. The problem is the drift. In the drift term, I cannot replace dKl by its symmetric part. There will be an antisymmetric part left over. Okay. Let's see what that means in a second. But for now, I can say, okay, if I replace dKl by dKls, then I will have a Ito Fokker-Planck equation, right? With some drift. I'm not bothered about the drift right now. There is some drift. There is some diffusion. This diffusion has the correct form. So I can write an Ito SD. Right? And the Ito SD will be okay, so I have the drift from the original ODE. I have this extra drift, which I have to think what to do with, whether D is not symmetric. Okay. And then I have this okay, so this is the SDE that we can derive in multidimensions. Okay, so once again, it has exactly the same, very similar form to what we saw in 1D, right? The drift comes in as it is. The coefficient of the fast fluctuating process comes in as a coefficient of the white noise. Okay, your dW is the Wiener process. Right? And now because I've written the Ito version, this is the Ito interpretation, right? No circle. So it's an Ito Brownian motion with this coefficient. The important thing is then the matrix, right, of the autocorrelation, integral of autocorrelation matrix, the D, where we had in 1D root D, now we have the effective root of the matrix D. Right? But it's not the full matrix D, it's only its symmetric part, of course. Right? And then we have the drift. So now in 1D, this D was symmetric. I mean, it was just one number. Right? Or in this case, if the D is symmetric, then I can do the same split here. Right? D can be nu transpose. One nu will go here, one nu will go there. I'll identify B into nu with the B into nu, and I'll say, oh, this is my Ito drift for Stratonovich. I'll get a Stratonovich equation. Okay, so this will become Stratonovich only if D is symmetric. If D is not symmetric, then this is not Stratonovich. And that's the surprising thing, that in 1D it's always Stratonovich, in multidimensions it is not. Right? It's possible to write it in some Stratonovich with some extra drift. You can do various manipulations of this. You can also interpret it as, where Stratonovich evaluates, remember, the coefficient at the midpoint. You can show that this thing corresponds to evaluation not at the midpoint, but at some shifted location. And that extent of that shift away from the midpoint depends on the antisymmetric part of D. So these developments are there in the paper by Bo and Chilani, but that's just interpretation. If you want to actually numerically solve the SD, you would write it in this Ito form, okay? Which you can of course solve. I mean, it's just a normal Ito equation with some drift which you add. It's only the interesting thing is the interpretation that that Ito equation is not Stratonovich. So you don't actually evaluate it at the midpoint. You evaluate effectively this B at some shifted location, which gives you this funny drift. Okay. So fine, that's okay. If you have some problem, as we had, right, OD with multidimensional noise, you take the white noise limit, you will get some Ito SD. Okay. The diffusion part of it will have the same coefficient that multiplies the fluctuating process, right? The square root, that coefficient. You will again get the autocorrelation, integral of autocorrelation matrix, the square root of that in the Brownian Wiener process. The only funny thing is your drift need not be the Stratonovich drift, right? Instead, what you have to do is this D, instead of being only the symmetric part, you take the full thing. But if you have to solve the Ito equation, there is no problem. This is actually analogous to 1D. Only thing is, in the 1D case, the Ito equation could be interpreted as being Stratonovich. Now you can't do that because this D is not symmetric in general. Okay, if it is symmetric, it remains Stratonovich. Okay, so if D so I'll say if and only if the D is symmetric, then we will have Stratonovich. Okay. So the reason to see this is, again, to summarize, not difficult. If the 1D derivation you extend to multi-dimensions, you get the same final Ito equation. The only subtlety is that the D is, if it is not symmetric, then the D can be replaced by the symmetric part in the diffusion term, but not in the drift. Okay, and therefore you have a drift which is not the Stratonovich drift; it's some other drift, right? Because of the antisymmetric part of the D. Fine. Okay. So now what I want to do is, after this mathematical discussion, right, discuss why or when is D not symmetric and what does that mean. Okay. So what we just had shown you mathematically that if D is not symmetric, then we are not Stratonovich, right? So, but the question is, what kind of physical systems will have a symmetric D and which will have a non-symmetric D, and are these corresponding to some generally physically relevant classes of systems? So for that, let's go back to what D is. Okay, so recall that Dij is really the integral right of, let me call it small gij, which I introduced earlier, and gij is the autocorrelation. Okay, yes?
I don't understand. When you say we are replacing DKL by the symmetric part, like, are we writing DKL as DKL S1 DKA and then like that A part is going to 0?
Yeah, so what you will do is you will replace DKL by, exactly as you said, A symmetric. So this whole term we will get with symmetric, plus this whole term with antisymmetric. Now when you look at the antisymmetric term, if you flip J and I, because that doesn't make any difference to the derivative operator, right? You can show that by using that property, you can show that that antisymmetric term must be 0. So you will get a result that this whole term with the antisymmetric must be equal to itself with a minus sign. You can show, because if you flip I and J, the antisymmetric term will be the same thing with a minus sign, right? And because this I and J is same as J and I, you can ultimately show that the whole term with the antisymmetric part is equal to itself with a minus sign. So then you can know it's 0. But that, of course, will not work here, okay, because you cannot flip these two bits. Okay, so that allows you to replace this by the symmetric part, only then you can treat this like a Fokker-Planck equation with a diffusion thing which is squared of something, and that something becomes the Brownian noise coefficient. Okay, so there is no problem continuing the result and getting some E2SD. The only problem lies in interpreting that E2SD now as Stratonovich, because that drift is not the Stratonovich drift. In the end, see, remember, all our mathematics is done only with E2. We started with an ODE, the alpha process we wrote as an E2SD, so that we can write the Fokker-Planck equation. Then we did everything in, Fenton manifold reduction, all that is done in function space. Then when we came back again, we used the E2 equivalence, right? Then final thing was to interpret it as Stratonovich, but that last interpretation cannot be done because this D is not the same as this. Right? This was the symmetric part, this is the full thing. Okay, so now the question is, when is this D, what is the symmetry or non-symmetry of D mean? So if you look at D again, it's the time integral from 0 to infinity of the autocorrelation function G, right, which is just alpha I at t and alpha j. So this would be symmetric if Gij was symmetric. Right? So if Gij is equal to Ji, then this would be symmetric. So let's look at Gij, right? That is by definition this. Right? And now I know that I can write this also, so it's a stationary process, right, alpha. What matters is the time difference, and having I here means I want to look at alpha I in the future. Right? But that could also be the same as this. Right? So the time origin starting point doesn't matter, it's a stationary process. You take one point, alpha j here, and alpha I should be in the future. So that is true even here. So these two things are equal. But now when I flip this, I'll see that this is equal to Gij at minus t. So Gij or t is Gij at minus t by definition. Okay, that's always true. Sorry, yeah, so it's Gji. Right, so remember, it's a two thing, right? I means I evaluated at time t, and j is evaluated at 0. That is the definition of Gij. I then said, okay, this quantity must be the same as taking j at some minus t and alpha I at 0. That is fine, right? Because what I'm doing is saying I is taken at a future time compared to j by an amount t. That is true here also. But when I go back to the definition, I must remember that the second index is evaluated at 0. The first index is evaluated at the argument of time. So therefore, Gij at t is Ji at minus t. So you have to do both things. And so therefore, you can see for symmetry, right, that now if Gij were equal to right, then we would have symmetry also. Right, because then I could use, so basically what I'm saying is the definition will show you that if you put t to minus t, you can flip the index. When you flip the index, t will become minus t. Right? But now if the autocorrelation of minus t is same as autocorrelation of t, then I can replace this by Gji at t, and then that would mean it is symmetric. So what we have said is that a symmetric autocorrelation tensor implies also the process is reversible. Right? Because what is the meaning of this, right? So we're saying if this is true, I will get a symmetric guy. So this means that if I take process I and j and look at their correlation, it's the same as if I done it in reverse time. So if I have a process, right, alpha 1 is affecting alpha 2 in the future. Now I run time backwards, right? Alpha 2 will affect alpha I backward in time. If those things are the same, then the process is reversible. So I'm not saying that necessarily, at this point, I'm not saying that I and j have the same causal relation. That means I affects j the same way jfxi. I'm not saying that yet. Right? What I'm saying is, even if let's for the moment not say anything about that symmetry, I'm just saying if let's say the large scale of turbulence affects the small scale in some way. If I run time backwards, the small scale will affect the large scale in exactly the same way. That would be a reversible process, right? Or in fact, right? So that is what we are saying here, right? Or what happens forward, the same thing can happen backward. The relationship between I and j, so the way I affects j forward in time is the same as if I had run the process backwards, right? So that is a reversible process. If process is reversible, you have no choice but for it to also be symmetric. Because the only way this can happen is if the small process affects the big process in the same way. That is what we have just shown from the definition. Yes? This? No. So that's what. So that I got confused as well. So remember the definition. So there are two steps, right? First, I look at the definition. The definition of Gij is alpha I at time t, alpha j at 0. So second index is evaluated at 0. That is part of the definition. First index is evaluated at this argument. Okay, so that is fine. Now I go from here to here just using what this quantity actually is, right? Which is alpha I is in the future. So I do that here. It's just that I call the future 0, so the past was minus t. Now I apply the definition again. I need the second index to be at 0, first index to be at the argument. So then I get this. Now I am saying, okay, so forget about the ij for the moment. I'm simply saying you take the autocorrelation, right? And saying that t can be replaced by minus t. So I can do that now here. I replace, if this is true, I can replace minus t by t. And then looking back, you'll say, oh, it is symmetric. Okay, so what we have shown is that if you have a symmetric autocorrelation, it also implies that the process is reversible. That means autocorrelation function is reversible in time. So in other words, reversible, you have some stochastic process which is reversible, right, multidimensional thing, then you will have it also be symmetric. Okay, now this result is trivial in 1D. Okay, so 1D we know it's always symmetric. And basically this tells you, which you also know, that if you have a stationary process in 1D, the autocorrelation function is symmetric in time. I mean, that is by definition, right? So if I have only a one-dimensional process, I'm going to say alpha at t comma alpha at 0. And that's the same as alpha at 0 comma alpha at minus t, and I can interchange the two immediately and I'll get it to be that g of t is g of minus t. That is immediate at 1D because there is no I and j, there is just alpha. So any one-dimensional process, when it is stationary, is immediately reversible. The statistics of the autocorrelation function, you can replace t by minus t. But that's of course because it's only one process, it is automatically symmetric. There is no other index. Right? So in 1D, this becomes trivial. In multi-dimensions, it's a non-trivial thing, right? So basically what we're saying here is you will get the Stratonovich limit only if the noises correspond to some reversible process. That means they are forward in time, backward in time, behavior is the same. This is of course not the case in turbulence. Turbulence is irreversible, right? The large scales, so we'll come back to turbulence again, but the basic idea in turbulence is this Kolmogorov cascade, right? Cascade of energy from the large scales to the small scales. So if you have a big fan stirring the air in the room, you're injecting energy at the large scale, right? And that, because of various fluid dynamic instabilities, breaks down and ultimately creates small scale motions. Okay, what you will not have in general three-dimensional turbulence is if you feed the small scale motions that you will produce some large scale circulation in the same reversible way. So the forward dynamics in time will not go backwards, right? So it's not reversible. And most non-equilibrium, I mean all non-equilibrium systems, right, which operated far from equilibrium are irreversible. And even beyond these macro dynamics, if you any problem that has a dissipation in it, input of energy will be irreversible. So all such processes, this will not hold. Okay, so the final point I want to make now is, so we've seen that in the multi-dimensional case, you can do the same derivation, okay? You'll get an E to SD but it will have a funny drift term that doesn't let you interpret it as Stratonovich. But you can still solve that equation. However, so then we are looking at what is that condition? If the autocorrelation matrix is antisymmetric, then it is not symmetric, then you will not have Stratonovich. If symmetric, you have Stratonovich. So now we are considering what does it mean for it to be symmetric, right? What is the restriction? So we just saw that it restricts us immediately to reversible stochastic processes. And if you know some basic statistical mechanics in physics, you will know that these reversible processes also mean that they are at equilibrium, right? Or say the other way, equilibrium processes, so you can have a stationary process, right? Something is fluctuating, but it could be fluctuating in a stationary state. That means statistics don't change in time, either because it is now at equilibrium. So you consider the thermal fluctuations in a glass of water, right, which is just left on the table, it's at equilibrium, there will be fluctuations. Those are thermal equilibrium fluctuations. But you will also have fluctuations if you are inputting energy and cooling it. Right? So you have one ball, you're sending an energy, other ball you're cooling. You will also get a stationary state with some linear temperature profile. Here also you will have fluctuations at the microscopic level. But this is not an equilibrium system. You will still get a stationary distribution of statistics, but that's because you're constantly driving the system and constantly dissipating. Okay, so the steady state need not be an equilibrium, right? We know this also in macroscopic systems. The way to distinguish is the flux. So if your system is at steady state and there is a non-zero flux of energy, of momentum, of mass, it is a non-equilibrium steady state. If the flux is zero and you have a steady state, that is the equilibrium state. So the same thing you can say for stochastic processes looking at the Fokker-Planck equation. So if I look at the equation for alpha, right, the Fokker-Planck equation in alpha space, I can again distinguish between non-equilibrium and equilibrium alpha processes, right, the fast correlated processes. Sorry, that is SD. Okay, so let me now look at the alpha processes, and my point is to see what kind of system is reversible. Okay. So this is the general Fokker-Planck equation, right, for these multidimensional alpha processes governed by some SDs, right? You have the drift term here, right, and the noise, and the diffusion term. Bij squared. Okay, so if Bij is in the SD, you will have Bij squared there. Okay, so now if you notice, I can write this as a flux. Okay, so the Fokker-Planck equation can be written in the form of the gradient of a flux where you have the advection flux and the diffusion flux. Okay, and I can have a steady state if there is a balance of fluxes. Okay, or I can have a steady state if the fluxes are all zero. So things are not cancelling each other out, means you have non-zero things that are cancelling out. That's like a non-equilibrium steady state. When things are completely zero, that is when you have equilibrium. Right? And so that zero flux condition is what corresponds to a process at equilibrium. Okay? There is no net probability flux anywhere in the system. Okay, so the other condition is for equilibrium. Then another thing that one can obtain from there, okay, which is also intuitive, is what's called detailed balance. Okay, so remember now this is actually the equation for the conditional distribution. Right? So the probability of starting with some alpha naught at 0, right, and then going to some alpha at time t, okay, the transition probability, that is the Fokker-Planck equation. Right? When you're at equilibrium and the flux is identically 0, right, you can also show that there will be a what is called detailed balance in physics. Right? And what this means is that the probability of going from some alpha to another is the same as coming back. Okay, so that there is no net movement of probability mass in time once you are at the stationary process. Okay. Now this is of course not the case when it's non-equilibrium, because non-equilibrium you could have net movement, but it's just that you are resupplying things. Okay, so you're constantly injecting or doing something to the system, driving it to maintain it at a steady state. But if you have stationary state, which stationary just means that the probability density is not changing, right? But it could not be changing because there's constantly a net movement of probability mass which you are countering, or actually there is no net movement. Right? So there's actually nothing happening, it's at equilibrium. Then you have this detailed balance condition, okay, which can be written like this. So I'll do it in terms of alpha. Okay, so what you're saying is that the probability of going from some alpha naught at 0 to alpha at time t, right, in your system at stationarity. Right, so this I'm using the stationary distribution here to calculate what is the probability of going from alpha naught to alpha t. Right, I take the probability that I am at alpha naught and go to alpha t times the probability of being at alpha naught. Right, so that is the stationary distribution because I'm assuming I am stationary. When I am stationary, is it equilibrium or not is the question, right? So if it is equilibrium, you will have detailed balance, and the probability of going from alpha naught to alpha, right, in a time interval t is the same of the reverse, right? That I start at alpha, whatever the alpha is, and I come back, right? And these alphas are vectors, right? So I can choose any combination of them, right? So some set of values you have for your different noises to go from here to some other set as the system evolves forward in time is the same as the back. Both are equally likely, and that also tells you it's reversible, right, immediately, and that's also the condition required for things to be at equilibrium. Right? There is no directionality in time anymore. It's all. But if you have a non-steady, non-equilibrium process, but still steady, this will not be true. Okay, so this is called detailed balance, and in fact, this is the condition one can use immediately to see that the autocorrelation function Gij is symmetric. Okay, so we'll see that in a second. Let's remember when we obtained this autocorrelation under the integral sign in our derivation, right? We actually encountered this kind of transition probability. So we had that L1 inverse operator. We wrote that operator in terms of exponential of L1 of t acting on, remember, alpha times Ps, and then we brought it under the time integral, and ultimately we said that exponential of L1t acting on something is just giving you the solution to the Fokker-Planck equation, right, with a different initial condition, and then we introduced this conditional probability. So actually at that stage, if you said that, oh, my alpha processes are equilibrium and satisfies detailed balance, we could have done the following. Okay. But I'm starting from reverse. I'm starting from what this autocorrelation is and rewriting it in terms of transition probability. Okay, so now I can distinguish the alphas with I and j. Okay. Let me put prime there. Right, that is the definition of the autocorrelation. So what I do is I'm multiplying alpha j with alpha I, right, and then taking the ensemble average. Taking the ensemble average means taking the average with respect to the stationary distribution. So what I do is I start with some alpha j and I take the average over the distribution of that alpha j prime. So I start with alpha j prime. In the brackets mean I take the average over the stationary distribution of the starting alpha j prime. Okay. So given that I start from alpha j prime, I then find the probability of finding alpha I. Right? So that involves this into the transition probability. And then to get this value here, I multiply with the alpha I. And then I integrate. Right? So I'm integrating over all the starting alpha j's weighted by the stationary distribution. Then the probability of finding the alpha I and integrating over all of those guys. Okay, so alpha and alpha j, of course, variables. Right? For each alpha j, I can get a different alpha I integrate over. That's how I get the autocorrelation. So that's just a definition. If you go back to your notes, this is exactly what we had in 1D. Right? So without the I and j, we obtain this result in our derivation and recognize that that is the autocorrelation. Now we are just, I'm coming back, taking you back to that point. Okay, now and if you use detailed balance, right, assuming the alpha is at equilibrium. Right, so you have some equilibrium process that is therefore time reversible and so on. You have detailed balance. So when you do that, you use this relation. Right, and this means I can write it as, right, the orders of these things don't matter. Right, what mattered was that alpha j was at the initial time and I took the stationary thing over alpha j, but that I can flip because of detailed balance, right? Okay, and the stationary distribution, of course, doesn't depend on time, right? So these things are same. Anyway, so if you look at the definition now, I just use detailed balance to replace this stuff. But now if you look at what I have, it is the same as the autocorrelation where alpha I is the initial point now. Right, and therefore this Gij is equal to Gji. And therefore the D will also be symmetric. So what I did here is just using the well-known detailed balance relation of the transition probability, right, just to show you the same thing, but it's also intuitively obvious, right? Once we see that having a symmetric autocorrelation requires you to have a time reversible process that will happen at equilibrium. Right? That is what this is saying, that whatever the dynamics are, they are time reversible. That's why if there's some probability go from some value of alpha to another forward, the same thing will happen. I can come, whatever value I got could also become the value I started with. And that just means that you cannot distinguish forward from backward. Right? So if I'm observing a turbulent flow and I start out with large eddies, and after some time I see small eddies. And if I wait some more time, again I see the same large eddies. How do I know that I've gone forward or backward in time? I could be playing that movie backward, it looked the same. The reason turbulence doesn't look like that is because if I start stirring with my spoon, right? If I take a cup of milk and I stir with a big spoon, I'll start seeing smaller and smaller things happen. Right? But I'll never start with small things and then get one big circulation. So immediately you know that there's an arrow of time and all such non-equilibrium processes. Because the reverse thing you never see. But a system at equilibrium, you cannot tell what is forward and backward in time, because whatever you see happening, some change happens in the forward, the same change will unravel itself as you keep going forward. Right? So both things are equally likely. That's what this says. And that immediately implies that there is no directionality in the time. Right? The dynamics must be reversible. But that is just showing you this, right, with the proof. By the way, in fact, you can use exactly this relationship. Instead of alpha I, alpha j, you put some function of alpha I, some other function of alpha j. You take it through this and you can show that in terms of the linear operator here, so if I call this whole operator L, L1 again, okay, this requirement of detailed balance, right, if I use this autocorrelation, I can prove that this L1 will be self-adjoint with a weight 1 by PS. Okay. And that fact I can use directly in my derivation, because if you remember, once again, I had to encounter this in the derivation when I did alpha. In the multidimensional version, it would be something like this. This was the integral we had to look at. Okay, and the difference, and then I was able to show that this integral is nothing but the integral of the autocorrelation. Okay, we had to do this integral. Sorry, d alpha, not. Okay, we had this integral, what I call T2, I think. In one dimension, there was no I and j, multidimension becomes this. For it, so this T2 is what became d in the end. Now it will become dij. It will be symmetric if I can flip the j and I. Right? And it turns out that when you have this detailed balance condition, which you can prove similarly, so if you have with detailed balance, right, L1 and L1 inverse is self-adjoint with respect to the weight 1 by PS. So what I can do is I can multiply and divide this guy by 1 by PS. Okay, this 1 by PS, I multiply and divided by this. This I keep like a weight. Then you will see that this is just an inner product, okay, with respect to this weight of this times L1 inverse acting on that. Because it's self-adjoint, I can flip this to the other side. Okay, so because it's self-adjoint, I can write this as right. And so I can effectively flip alpha, then finally I will get integral alpha j okay, so I can start with this and I can interchange the j and I because of the self-adjoint property of L1 and its inverse in the 1 by PS inner product. But that property happens only under detailed balance. In fact, to prove that, as I said, you can just show this is basically, instead of taking autocorrelation of alpha I, alpha j, I take some function f of alpha I, g of alpha j, and I use some properties, I can show this. Okay. But again, even without going there, you just use detail balance here directly and we'll get what we want. All right, so if you've not, I mean, these are just some extra details for those who are familiar with equilibrium statistical physics, okay, and the behavior of the Fokker-Planck equation at equilibrium. You will be able to connect these different ideas to the fact that the autocorrelation function is reversible. But the upshot is finally that if you have some slow process, okay, being driven by multidimensional, many different fluctuating signals, and I want to take all those fluctuating signals to the white noise limit. That means I'll have a process driven by many different white noises in that limit. Okay, so whatever coefficients you have stuck in front of those fluctuating signals in the ODE, they will be the same coefficients sitting in front of them in the SD. Okay, but that SD will not be Stratonovich in general. It will be Stratonovich only if those different white noises, if you look at their autocorrelation matrix, if it's symmetric, which also means the fluctuating processes are time reversible and interact with each other the same way. So that is highly restricted, right? Because you are imposing so many symmetries in time and between the processes. So really this will happen physically only when you're looking at there is something happening and it's being driven by some equilibrium-based noise, not when it's being forced by a non-equilibrium process. So to give you a concrete physical example, you imagine you have a thin film of liquid, okay, and it's sitting on a table. Okay? And if it's in a macroscopic description, I will just look at the film and I'll just write Navier-Stokes equations for the film of liquid. Now there are two ways in which I could introduce fluctuations into this. So I'll have a mean height of the film, for example. Right? And if there's no noise deterministic, I'll just have some equation for how the height of the film is. If I shake it, maybe the film will distort. But that's not noisy, that is deterministic. Now I can introduce fluctuations in two ways. One is I can say, okay, that actually if I zoom into the interface, it will always be fluctuating because of thermal noise. Even if I leave the film in a beaker on a table by itself and I zoom in, I will see the interface fluctuating. That's because all the molecules in the liquid are undergoing Brownian motion. But this is an equilibrium situation. So if I wanted to model the fluctuations of the film when it is just sitting by itself, right? So those fluctuations are being driven by thermal noise at equilibrium. So then if I write some effective equation for the height of the film driven by thermal equilibrium noise, then this situation will hold. I'll have detail balance in the noises. I will get the Stratonovich. I'll get some kind of Stratonovich SD. So I'll have the deterministic part coming from Navier-Stokes for how the interface were to evolve if I shook it or I did something to it, right? And then the noisy part, which is just coming from thermal motion, that would be Stratonovich, right? In some appropriate form, right? But that's a situation where the noise is coming from equilibrium fluctuations. On the other hand, if I took the same film and I said, I'm looking at doing large scales, I'm always zoomed out. I don't care about thermal noise. But now I have turbulent air blowing over this film. Okay? So now the film will fluctuate because of the wind, turbulent wind, because it's exerting fluctuating shear stresses. Of course, I can write full equations for the air, but if I don't want to do this, I can model it as only equations for the water in the film plus some stress which is fluctuating, which I model. Right? Now, those fluctuations are not from an equilibrium process, they are from turbulence. Right? So that is not reversible. Right? If there's, in the wind, there are some big eddies in the wind, as you go forward, they'll become small eddies. The reverse will not happen, for example. Okay? So wind-driven films would be non-equilibrium noise driving a process. Now I can still decide for simplicity that I'm going to replace turbulence with some noise whose autocorrelation is symmetric. And then I would get Stratonovich, but then I know I'm making a big assumption, right? I'm throwing away the non-equilibrium aspect of the turbulence. Maybe it doesn't matter for what I'm interested in, maybe it matters, but I should remember this. And if I decide to do non-equilibrium, then I know the autocorrelation function is not symmetric. I cannot take Stratonovich interpretation. I should take the SD with the full autocorrelation matrix. So, okay, that's just something to keep in mind. Also, later in the course, when we do some derivation, we will in fact blatantly replace turbulence with a reversible kind of noise. But then whatever results you derive, you should remember that those results are assuming quite wrongly that the turbulence is reversible in time. Right? So that already gives you a clue that if your real life turbulence behaves differently from what your stochastic model tells you, maybe the reason is that you have neglected the fact that turbulence is far from equilibrium. We'll see some of these things when we go to turbulence, which in fact we will do in the next lecture onwards. Okay, thank you.